Usually a big utility that we have in textile sector is the steam system. And usually when we go to the steam boilers, we do an initial assessment. So boilers that are old boilers, for example 15-20 years old, or the fire tube boilers which have only one or two number of passes, then boilers that are using coal or biomass, these are usually the ones that have a lot of inefficiency issues. Then larger boilers, 20, 30, 40 tons per hour boilers, and who don't have economizers or air preheaters. Even boilers with 5 or 10 tons per hour have big saving potential if we install economizers or air preheaters. But these economizers and air preheaters become even more cost effective and even more feasible when we have bigger boilers. The boilers, when we have these boilers of 25, 30 or 40 tons per hour boilers, we also need to see why the factory is still using low pressure or not using superheated steam and producing energy and only producing steam separately and power separately. Then there are some fire tube boilers that used to be used in the garment process because they needed less small amount of steam, but these are very inefficient, usually not used in the textile process anymore. If there are boilers which are backup boilers, so usually factories have 2-3 boilers installed, one or two are running and one is standby, and these are also connected to the common steam header. These are critical points. So what happens is that because they are connected to the common steam header, the main tank of these boilers also become headers because there's backflow of the steam. So a lot of condensation also takes place. Companies do not apply a blow down to these boilers usually, but these also sometimes need blow down. Usually it is recommended that if there's a boiler which is usually on standby most of the time, install a solenoid valve that shuts down its main line so that there's no back pressure going from header to the boiler. Typical questions that we need to ask are, what are the temperatures that are required in the process? So if the process is requiring 60, 65, 70 degree temperature, why do we even make steam? Why don't we just heat up the water, use these equipment or use water heaters or solar water heaters, for example, instead of boilers, and directly feed hot water to the machines? That would reduce the heat exchange time and produce hot water. This is one question that we need to ask. So anything less than 110 degree, 100 degree, if all the processes are there, then we also need to explore this possibility. And then also need to see what is happening inside the boiler. Is it a single pass boiler? Is it a multi-pass boiler? How is the heat exchange taking place? If it is a solid fuel, what is the size of solid fuel? Is the solid fuel already lost in the bed because it has a lot of fine grains in it, for example? Is the fuel coming out properly burnt or not? Is there any calorific value in the ash that is coming out or not? So these are the things that we also need to have a look at. So this is an energy balance of a boiler which I generated using this tool Meyer. So I also wanted to introduce you to this tool. I will show you what it looks like. So my suggestion is that you download this tool Meyer, which means manufacturing energy assessment software for utility reduction. This is typically for utilities, not for the production processes. And when you install it, this is the main screen that you see. You can create an assessment. So you can start creating and then upload your data. And in this, you can do pump assessment, process heating assessment, fan assessment, steam assessment. Then you also can do some try your hand. So there are some small calculators that can be used. Wastewater assessment can also be done using this. Some other calculators, you can see there's some general calculators, process cooling, process heating, compressed air. So they are actually improving their compressed air tool. If you go to their website, you will see that they're improving this tool and they're adding some more stuff here as well. Fans, lighting, motors, wastewater, steam pumps, inventory management is also there. So there are different tools that there are there. Some examples are also here. If you open any example, you will see how they have done some assessments. Then you can do data exploration using these different tools on the left hand side. What I did was that I created one assessment of a steam system to show you in this process. So when I open it, I will show you direct take you. This is where it takes us. So system setup, it asks you what you want to do, which currency do you want to use, which units, empirical, metric, or others you want to use, and then it sets the units here. You can add some notes here. For example, this one was a 30 TPH boiler but was operating at 19 TPH. Then we click next and it takes us to operations. Here we can set operating hours, how much kilowatt of electric power it is importing, that is what we can write here. Temperature of makeup water that we are adding. Then the cost of fuel, cost of electricity, and cost of makeup water in dollars per liter, because I selected US dollars as the main currency. Then I went forward and I selected the type of fuel. So I selected solid fuel because I was using typical bituminous coal. The boiler combustion efficiency came from the stack analysis. And the blowdown rate was based on the data that was provided by the site engineer. And yes, the blowdown was being flashed. They were not directly doing anything, they were just flashing it. And they were not using blowdown to preheat or the makeup water. Steam temperatures were 176 degrees. Deaerator vent rate was 0.1%. And the deaerator pressure was 1 bar. So it was actually 1 bar gauge, not 1 atmosphere. Then we went forward. I applied the header. So there was only one header. The condensate return temperature was 95%, and they were not flashing the condensate. So it was directly going to the deaerator and condensate recovery tank. Then the pressure of the high pressure header was 8 bar. Process steam usage was 19 ton per hour. Condensate recovery rate was 10% only in this case, and heat loss in the header. So the temperature difference in percentage from inlet of the header and outlet of the main header was 0.1%. You can also take help here in how to calculate these things generally. Then turbine, so this boiler did not have a condensing turbine to power energy. So this I unchecked and I moved forward. When I moved forward, it brought me to the assessment where we can see the diagram. So it shows you some points where the saturation is taking place. For example, it shows you how the steam is going, where it is being converted into condensate, and where is the flashing taking place, what is happening in deaerator. So everything is there. On the right hand side, we have results. So the operating costs are there, fuel consumption, gigajoule is there, electricity generation, import, makeup water quantity, cost. And if we click on view more cost details, we also see total operating cost here as well. So there are different, we can also calculate marginal cost. So there are different costs that can be calculated. Based on this, we can go to report. In the report section, we have the values in terms of percentages and amounts. We have an executive summary, we have losses calculated, we have the diagram. Report has a graph, have certain graphs also there. So out of total input energy, how much is being used in process, how much goes into unreturned condensate, how much goes into stack losses, and how much goes into other losses. So these are the saving opportunities that we have here, which can be recovered. Then the input summary, what was the data provided inside, some facility info which we did not provide in this case, and a Sankey diagram. So because we only did this assessment for the baseline, it provides us the Sankey diagram only for the baseline. It shows you how much total energy is going in and where is it being used. So process usage, unreturned condensate, returned condensate, blow down losses, other losses, stack losses, all put there together. And if we click print, all these sections get printed into a report form. This Sankey also shows on top in the Sankey section. And if you go to calculators, you can have multiple calculators there. So you can do a calculation for boiler, deaerator, flash tank, header, heat loss. So all the data that we put there, if we don't have the data, we can also do a calculation here as well. So a wonderful tool, I really like it. Some drawbacks is that it estimates the fuel intake itself. It does not let you to enter the actual amount of fuel there. It also does not let you select if you are doing during any heat recovery from the stack. There are no options of doing that in the main assessment. So these are the two main drawbacks that I have seen. Third is that because we have selected the solid fuel, it has not provided any option of doing assessment for the filtering process or the water showering process to remove the pollution load or calculating the greenhouse gas emissions, for example. These are the things that are missing. But since we are all experienced auditors, we can use this assessment here and do some of the calculations manually and club them together. So the report can be generated pretty quickly rather than we use a lot of Excel. We can use this and then generate the reports very, very quickly. So if you go to energy.gov, this link I will share, it shows you this energy.gov/ERE/AMO/Meyer. Meyer is without E at the end. Please remember that. So if you scroll down, it gives you different introduction to this one, tool summary. So I went to this link, and in the bottom, if you scroll down, so this is the link that worked, Meyer setup 0.9.2 beta.exe. So do download it, use it during next days. This is how I developed a flow diagram of a 25 TPH boiler. You can develop this yourself pretty easily. It took me only 10 minutes to come to the point where I was able to develop it because I already had all the data available. So very easy. If we have to do it manually using eSankey or other software, it takes maybe 3 or 4 hours to do it. And then boiler efficiency analysis. I mean, on the left hand side, I did an efficiency analysis based on the total fuel consumed and total steam energy generated. On the right hand side, efficiency is provided by a stack analyzer. And you can see that on different stages of the burner, the efficiency was different. For this boiler, efficiency on low fire was 81.6%, whereas efficiency on 25% damper position or 50% damper position were lower. And even at high fire, the efficiency was lower. The boiler was generally running in high fire condition, not in low fire condition. Recommended that the factory that they do an optimization, do install a VFD, install an oxygen sensor on the exhaust, and with that oxygen sensor and temperature monitoring of exhaust, they loop back to the VFD, remove the dampers inside the ID or FD fan, and optimize the efficiency. One question: why is there a difference of efficiency in the left-hand side and on the in the left-hand side calculation and in the stack analysis? The thing is that on the left-hand side, it provides us overall efficiency for the total steam consumed and the total energy in the total energy in the fuel. On the right hand side, it is only providing combustion efficiency. based on the flue gas temperatures, oxygen content, um, and moisture content, as well as ambient temperature. So it does a stoichiometric efficiency calculations inside the tool. So these are two different methods. A stack analyzer only provides you efficiency of the stack of the combustion process, not the whole boiler. So that is why there's a difference. So I recommend that you calculate both efficiencies usually, so that we have a real value. Then what we do for solid fuels is that we also do an efficiency analysis of unburnt carbon in the ash. So the coal, we did the coal analysis. Its GCV was 5914 with fixed carbon of 51.21%. The ash that came out had an unburnt carbon of 15.47% and GCV of 1412 kilocalorie per kilogram. The total ash residue was 18%. And if we use this formula, total ash collected per kilogram of coal fired multiplied by GCV of great ash divided by GCV of coal fired, then we can calculate the total efficiency loss. So you just have to put in the coal analysis and ash analysis, and then it automatically calculates how much percentage of loss we're making. What I usually do is I provide allowance for unburnt carbon, about 5%, because we cannot do an ideal zero unburnt carbon. And then we can have a possible efficiency improvement based on this. And then blowdown, I mean, we're all aware of the automated blowdown. People are very, very hesitant, but you can see this factory was doing a manual blowdown. And according to them, they had made an upper control limit of 3000 TDS and lower control of 2500 ppm for TDS. They wanted to keep the boiler blowdown TDS within this range, but you can see the actual values that are there. I can only see 1, 2, 3, 4, 5, 6, 7, 8 data points among all the data points within that range. All of them are either above or below. So when we have higher TDS, that means we missed out on blowdown. Blowdown should have been done earlier. When we are near or below the lower control limit, that means we are doing too much blowdown. And then we are losing a lot of energy in blowdown as well. So if we have automated controls, then the blowdown would also be within the limits. And also the quality of steam would also be within control. Then typical network issues. This one factory, we saw that the boiler was operating at 9 bar. There was no pressure reducing valve, but still the pressure, average pressure we were reducing in the 3 sections were 7 bar. So there was a lot of pressure loss in the piping, in the bends, and in the walls. There were some leakages as well. There were some uninsulated lines which are also contributing to condensing. So these are the issues that we saw. Pressure, we keep on increasing pressure to compensate these losses, but it's better to install pressure reducing valves. Then wastage of condensate takes place. You remember this in the textile case story on day 2. We saw that this company did not install a condensate recovery system because this machine was very far away from the boiler. This is a true case I have seen many times. And sometimes the condensate lines are lifted. So instead of recovering condensate by gravity, they, without installing pumps, install condensate lines on top. So after the steam trap, the line is going towards the roof. That is where the piping is done, old-fashioned way. And they think that with the pressure of steam, the condensate will be lifted automatically. What happens is that the condensing takes place, it puts back pressure on the steam traps, and in turn the steam traps stop working. And then at the condensate recovery tank, we see this kind of a flash steam. You can see this is a very, very long plume of flash steam going out from the condensate recovery tank, which shows that the steam traps are not working. Then obviously this we are all aware of, the losses because of uninsulated lines because of leakages, because of absence of pressure reducing valves. These are the points that we need to look at generally. And then I saw that some companies use condensate in the waste heat recovery boilers. It actually reduces the waste heat recovery rate. So feed fresh water to waste heat recovery boilers and feed the condensate to actual boilers. That is what we should do usually. And then we come to thermal oil heaters. You see some small fire particles on top where my cursor is. Do you notice it, or is it very dim for you to see these small flashy particles on top? Do you see it now? This is coming out of the stack of an oil heater, and this is a furnace oil fired thermal oil heater. It's not a biomass fired thermal oil heater. So we thought that maybe the spray nozzles of the burner are not working properly and they're spraying too much oil, furnace oil for burning. And maybe this is going out as particles, and when it comes out, it starts burning. So we had to actually open everything, and we figured out that there was a lot of soot accumulated in the exhaust. It was so much accumulated, then it started coming off and going out. And since the temperature was very high, when it came out, it started flashing in the air. And this is, by the way, a paper mill. Anything could have happened. So we immediately had to shut it down, get it repaired. So the whole system was cleaned, and they did not have any record of cleaning the suit. So their maintenance practices were not up to the mark. So we did this, developed maintenance practices and improved this as well. Highly satisfied client, I must say. The question is, why do we need thermal oil when we already have steam boilers?
So for the thermal oil heater, I think the reason is in the factory, we may need, there are some process that need a high temperature. So with the available steam source, they cannot meet the demand. For example, we need up to 200 Celsius degrees. So if we use the boiler, then the pressure will be very high. Maybe so. For the boiler is around 8 to 10 at, so it cannot meet the requirement of a high temperature as the thermal oil heater supply.
And when you're using steam, there's also condensing that takes place. We do not want any condensing taking place in these kind of processes where we have these processes where we're using drying. So that is also one of the reasons. Also, to be able to, you said it correctly, that to be able to exchange this much amount of heat that we're using with thermal oil, we need very high pressure steam, and we might need more steam than with energy in steam than we're using for the thermal oil. So typical issues, same as steam when we talk about network: uninsulated lines, air to fuel ratio, excess oxygen, working mode, if it is working at full fire, low fire, high fire, is it modulating or not modulating? Usually they are not modulating, but they should modulate, not only between high fire and low fire, but also in between. So based on the temperature that is required in the process, they should modulate the thermal oil heaters. As I said earlier as well, that if we need 200 degrees Celsius in Stentor, we need 250 degrees Celsius in the thermal oil. Then talking about the air fuel ratio, managing air fuel ratio in thermal oil heater is not as simple as in case of steam. Anyways, even if it is a boiler or if it's a thermal oil heater, it is important to contact the manufacturer or look at the design data. So recently, for example, a thermal oil heater, we thought that we could bring down its excess oxygen from 8% to 3%. So we discussed with Inplan, who are the manufacturers. They said that this equipment that you are looking at is optimized between 4% to 6% oxygen. So we suggest that you modulate it between 5 and 6%. So we had to revise our calculations based on that. So instead of suggesting 3%, then we suggested 5% excess oxygen to this company. So that is what we also need to look at. And then we already discussed this point of how much in additional degrees we need in thermal oil heaters, and also having a look at how much temperature thermal oil is giving up while returning back. If at the oil heater we're only getting 2, 3, 4, or 5 degrees of delta T, that means we are overheating the oil. Then safety, because it is a pressure vessel, but unfortunately these are not inspected as pressure vessels, because in Pakistan they do not consider by law oil heaters as pressure vessels, and we have seen many accidents taking place in few years. Then power generation, I hope you are well aware of the heat recovery potentials in the power generation system, where we can recover heat using a waste heat recovery boiler. We can install another condensing economizer or a simple economizer on top of a waste heat recovery boiler to recover further heat. So heating up water for process. Then the jacket water or engine cooling water can also be used to operate absorption chillers or to supply hot air for the processes that bring in significant thermal energy savings. So this is a flow diagram that is provided by the equipment manufacturer of a 3.4 megawatt engine running on natural gas, and it shows different areas where the heat is dissipated. So this is the water cooling cycle, this blue and red, and all this cycle is going through the cooling towers. And what we did was we did a calculation for jacket water heat recovery system, and you can see that the payback is only 9 months, because it would reduce significantly the amount of steam required in the processes, and also increase the process output. So what we do is we use the flow rate of the jacket water. Then we see how much delta T do we need on the jacket water side, and how much delta T we can gain on the demand side using the Q is equal to MCP delta T and using the heat exchanger efficiency. So Q on the left hand side is equal to Q on the right hand side with an efficiency of the heat exchanger. Okay, so the recoverable heat on the right hand side might be a bit lower than the heat that is available on the left hand side, and this water flow rate on the demand side needs to be calculated based on the demand side flow rate. How much water do we actually need? And if we need less water, then we'll have high temperature water. If we need high water quantity, then we will gain less water at the hot water at the outset. So using the Q is equal to MCP delta T, we can directly calculate the saving potential that is there. Typically for this 3.4 megawatt engine, we got a quotation of 165,000 USD, including the investment for automation of cooling tower. Because if we do this, we also need to automate the cooling towers, just in case we have sometimes low demand of the hot water in the processes. The cooling towers must directly kick in at that time and start doing the cooling using the cooling towers rather than using this heat recovery system. A waste heat recovery boiler can also be calculated in the same way. Again, Q is equal to MCP delta T is used everywhere in all the thermal processes. Quite similar passion. I think we don't need to go into details of this calculation. Very similar calculation. A big amount of greenhouse gas emission reduction can be achieved here. Similar calculation for normally these waste heat recovery boilers, they bring down the engine exhaust temperature to 150 160 degrees Celsius. This is still recoverable. Then we can install a normal economizer, which can bring it down to around 100 degrees Celsius, or we can install a condensing economizer, which is more expensive, but then it can bring it down to 60 degrees Celsius or 50 degrees Celsius. intentionally doing condensing in the system, recovering carbonic or whatever acid that can be produced depending on what is our fuel intake. So in case of natural gas intake, we get carbonic acid. This carbonic acid can be used in the ETP for neutralization process then. So bringing in savings not only by recovering energy, but also bringing in savings because of ETP reduction in chemicals in the effluent treatment plant. It is advisable to feed hot water to this system, not directly cold water. So we can use kind of a little bit of water preheating system around 70 degrees Celsius, and then we can get water at around 95, or even if it is a pressurized system, we can even get water at 100 degrees Celsius. If it's non-pressurized system, then 95 to 98 degrees Celsius is easily recoverable. But this hot water flow rate must be according to the need of the hot water. If we don't have any need of hot water in the process, there is no need of installing the system unless we can use it in the boiler, for example, for feed water.